Okay, so the next topic of our discussion is the scattering in a central force field. As we remember, last time we had solved the Kepler's problem, which was essentially an example where an object orbits around another object into a potential which has a minimum, essentially which was a bound system. But now we are going to study a situation where the we don't have actually where the objects fly off. So remember we had drawn three diagrams for the cases where we had different kind of energies. In one case, the total energy was greater than the effective potential. So this is going to be the case for our case. So before that, let's discuss so what scattering is. So scattering is essentially, so you are already aware of what is known as the collision. So collision is a phenomenon where two objects, two objects collide directly with each other, and then they scatter off along different directions. Our scattering differs little bit with the collision in the sense that during the scattering, one object may not hit another object, rather these may influence each other. So essentially you could say that scattering is essentially a phenomenon of influencing an object, of establishing influence of one object with another. So now, depending upon whether the energy remains conserved or energy is lost when an object hits another, the scattering could be divided into two forms. Like that, the first case where the energy remains the same as it is, and therefore the velocities of the incident particle is called the elastic scattering, and the other example is called the inelastic scattering. So let me first, so in this scattering could essentially be understood by finding out the cross section which gets affected of the target particle by the incident beam of particle. So let me first draw a picture where I will have a beam of particles, that's called the projectile. So imagine these are all the projectile particles, that's the beam, and some of these are essentially moving towards the target. So you have the target and the beam. So these are the incident beam of particles. Okay. So this is also called the projectile. And imagine that you have a tiny area of this whole thing, and imagine that one of these such beam or one such particle having mass m hits at a distance s with respect to the center. So say this is the distance s and this is the thickness of this projectile. So now obviously due to the influence of the force, this object, so let me draw first a line that passes through the center. So this will go like this. So now it will keep moving until there is no influence of the force. That is, these are infinitely separated, but as soon as it reaches into the area of influence, the path of these objects starts getting diverted, and therefore you would see a situation like this. So now if you so initially there would be an influence, the path will get affected, and the object will keep flying. Now, after moving a significant distance, that is once again when it reaches the limit of infinity, you would again see the object moving into a straight path. So now we could draw essentially an asymptote from here to a point that joins the center. So then this angle made by the final direction of the beam with respect to the incident direction or the center, that is called the scattering angle. Okay, so because this is a beam, so it will essentially affect a whole lot of solid angle. So this whole strip, so this is essentially going to give you the, so this is going to be the sigma omega, which is the scattering cross section, and this is going to be the whole solid angle d omega. Okay, so let me tell you what this is. So this is essentially the d theta or d omega rather. So what is the total cross, so scattering cross section, as we just said, scattering cross section. So this is essentially also known as the differential cross section. So this is given by the following formula then. So this is essentially number of scattered particles per unit time per unit area divided by the incident intensity. Now, obviously, what is this incident intensity? So the incident intensity is nothing but this is the number of initial particles per unit area per time. So this is also called flux density and is represented by a symbol I. Okay, so now let's see what is happening around here. So imagine if we assume, in fact, V to be the energy particle, the speed by which speed of the beam particles, and m to be the mass of the projectile particle, what we could infer? We could write the angular momentum. The angular momentum that would be mb naught s, because as you could see, this s is essentially a direction. So this is like something like this way they are hitting, so it's hitting normal to the direction of the motion, and the s is the distance at which it is. So now, because this is a phenomenon that is governed by the central force motion, so this whole phenomenon would be actually happening into the plane, and as we had already seen in the previous lecture, that the total angular moment, the angular momentum is going to be a constant of motion. So this is the initial angular momentum. Of course, this would be equal to 2m e. So this is going to be mb0 is going to be root 2m e and then s. Okay, so that would be the angular momentum that we are looking for. Okay, so let me put this as number one. We will discuss about this little bit more detail later. But before that, let's check actually what would be the formula for the scattering cross section. Okay, so what we could check, we need to essentially, as this is a classical scattering, so the number of particles, number of the incident particle and the number of particles that are leaving after the scattering, that should be the same. So what does it mean? So if we assume as the incident intensity is this S, and as we had seen that the number of particles that are hitting are essentially into this area which is given by the strip of thickness ds and a radius s. So this is going to be this number of particles. So number of incident particles that should be equal to the number of scattered particles. Now, number of incident particles. So obviously, the area is going to be 2 pi s and ds, because the strip will have a perimeter of 2 pi s and it has a thickness s ds. So this is going to be 2 pi ds, and that should be equal to I. On the other hand, we will have sigma omega and then d omega, c omega, and the d omega. Okay. So this is the solid angle d omega, and then of course the intensity. Now sigma omega d omega could also be written as sigma theta, and d omega is the 2 pi sine theta, where theta is the scattering angle, d theta. Now i's would cancel, 2 pi's would cancel as well. So therefore, the scattering cross section sigma theta is given by S, the formula S upon sine theta, and ds upon d theta. And because you know that this is cross section, it should be positive, and therefore we would just write sigma theta is equal to S upon sine theta ds upon d theta. Now this is the formula for the scattering cross section, and the total cross section could then be written using this particular formula as follows. So this is sigma total, that should be sigma theta, and then d omega, which is just 2 pi sigma theta sine theta and d theta. So this is going to be the formula number 3. Now what we realize, what is S? S is essentially the distance at which an object hits. So this should obviously be a function of theta, the scattering angle. This is essentially called the impact parameter. So this should be a function of theta and the energy of the incident beam. So that means if we could get the equation for the S in terms of theta, we should be able to get the value of differential cross section, and thereby the total cross section could also be obtained by integrating over the whole solid angle. So now, after getting this idea, we will get back to the kind of scattering we want to study over here, and we'll try to have an idea of the total cross section for the kind of scattering that we will have. So the scattering that we are going to study is essentially the called the Rutherford scattering. But even before that, let me give you something interesting out here. So remember, I just made an interesting picture. What was happening? So we had a center, some object was hitting, then due to the influence of the central force, this object was leaving at a direction theta with respect to the original direction. So what we had said, that this is the scattering angle. So this is called the scattering angle. Now, obviously, if we draw a perpendicular from here, this whole thing would be divided into equal angles. So we will refer these by something called psi. So this is going to be the angle by which the object would have orbited, or the incident angle. So this is called the incident angle. So if the objects would have been bound under the central force, we would have seen the objects being orbiting. The equation of orbit would have given in terms of psi. So now essentially we are ready to relate the two phenomena, that is the scattering phenomenon and the phenomenon of Keplerian orbit, by this incident angle. Now one more thing to remember, that the direction of this sign differs by the direction of the theta that we had taken in the previous problem by an angle pi. So we will adjust that, but even before that, what we realize that psi from this equation, we have this interesting form. So this is psi plus theta, that should be, total should be pi, and therefore theta should be pi minus 2 psi. So this is my equation number 4. So now we are ready to study the Rutherford scattering. Ford scattering. So what we have in the case of Rutherford scattering? So remember F Rutherford. For Rutherford scattering, the force is given by, so we have some object, the alpha particles, which have the charge Jd. This is hitting the nuclei having the charge H prime E prime, and the force is proportional at a distance r, so this is going to be this. So this means we could write this as k by r square, with k being minus zz prime e square. So that is all we have. So with these kind of substitutions, we should be able to write the equation of orbit. Well, this is not orbit, is given by, how will we give the equation of orbit? So we will write the equation of orbit as d psi is equal to, so obviously we could have d psi is equal to dr, it is just same as before, ldr by r square, square root 2 mu. Now I will write this mu and then e minus v minus 2 mu by, in fact we could write L square over here. So this is going to be 2 mu by L square e minus v, and then we have minus 1 over r square. So that is the form we have. And then this differentiation limits would be 0 to psi. It will start from 0 and go up to the psi. And now we notice that at psi, we also have certain distance. At psi is equal to 0, we have some minimum value, and then ultimately the r has value equal to infinity. So that is the kind of integration we would need to solve. So next is going to be, therefore theta, which is equal to pi minus 2 sine pi minus 2, and then the psi, which is going to be dr by r square, square root 2. Now since mu is going to be approximately equal to m, so I will just write 2m e minus v by L square minus 1 over r square. Now I will make a substitution from our previous discussion. So remember, L was mb0 s, which was root 2m e and s. So from here we could simply use the value of f, and by doing that we should be able to cancel something. So this is going to be pi minus 2 This is going to be dr by r square square root e 1 minus v by e. That is one thing. And minus, then we will have minus, minus we will have, minus would be, in fact, because we are derived, so this should be L square by minus L. So this is going to be root 2 Ne. So this is going to be root, sorry. Okay, so anyway, we will solve this integration into the next lecture. Okay, bye for now.